Now going over to question number 7. This is particularly challenging because the grand majority of the time, when you have a graph involving time and distance, which here is in miles, in most situations, the x-axis would be the time and the y-axis would be the distance. But what's happening here is the total opposite, because x is the number of miles and y is the number of minutes. And I'm assuming that because I know that x is the opposite. So if x is the miles, y has to be the minutes. So now in the graph on the left, the slope here would be the change in y over the change in x, which is the change in the distance, which is miles, over the change in the time, which is minutes. And you do hear that more often. Miles per minute, miles per hour, that's more common. But in the graph on the right, if we're dealing with the slope there, well, that's the change in y over change in x, because that's what slope always is. But here, that's the change in the number of minutes per the change in the number of miles. And so it's just very much more uncommon. And so you want to be paying attention to that distinction here. But Juan is writing 5.7 minutes for every 1 mile. So 5.7 minutes for every 1 mile. And so that's the slope in this sense. So if we're doing y equals mx plus b, we know that the m is now 5.7. So we have like y equals 5.7x. But we're also not being told that but also keep in mind that we're not being told a starting number of minutes. So this didn't start at 2 minutes or anything like that, which would have the graph looking like this. Instead, we're starting at, of course, 0 minutes. So it's a nice graph, even though the x and y axes are in kind of a backwards place. But the equation that looks like ours is answer choice D here.